Recently, I've been experimenting with active learning. I think it has the potential to make parameterizing steps of seismic processing more efficient. Many steps of seismic processing require parameters that vary over the dataset. Choosing these parameters is time consuming and labor intensive. If we can make it faster, that would save people a lot of time. I'm going to describe what active learning is and why I think it's relevant for seismic processing. I'm then going to describe my implementation of active learning for one step of seismic processing. That step is first break picking, but even if you aren't interested in first break picking, I hope this will still be useful to you and that it might help you to see how active learning could be implemented for an application that you are interested in. In the machine learning tradition, I'll begin with a cats and dogs classifier. The definition of active learning initially sounds quite like that of semi-supervised learning. Imagine that you have a collection of cat and dog photographs and you wish to label them as cats and dogs. You've already labeled some of the samples, and now you wish to train a model to correctly label all the rest of them. The difference with active learning is that it assumes you have a way of labeling more of the samples. It's referred to as an oracle, and it's usually just a human who you can show the photograph to and ask them, is it a cat or a dog? The goal of active learning is to optimally choose which samples you show to the human for labeling, so that you can learn to correctly label the whole dataset after asking the human to label as few samples as possible. You could even start with no labeled samples and then use active learning to build up an optimal set of labeled samples. It's an interesting problem, and you can probably see why this is relevant for seismic processing, as it's a very similar situation. We have a large amount of data that we wish to label, where for us, the labels are the processing parameters. We also have a way of labeling more of the samples. We can show a sample to a human operator and ask them what are the appropriate processing parameters for this sample. The optimal parameters often vary from trace to trace. If you're parameterizing a denoising tool, then for a noisy trace, you probably want to use parameters that are going to result in stronger denoising. But datasets are generally too big for us to label every trace with the right parameters. Currently, this is often handled by having the human only select the parameters on a regular grid of samples covering the dataset. These values are then interpolated to estimate the parameter values at the unlabeled points. There are two problems with this approach that I think active learning can help with. The first is that the data may not vary much over large stretches, and so the same parameter values might be appropriate. It's thus not a very good use of time to choose the parameter values on those points, as you're not providing a lot of extra useful information. The second problem is that if the parameter value changes abruptly, then until you get to the next grid point, you're going to be using parameter values that are quite far from optimal. You could get around this problem by having a human look through the dataset to select which samples they'll choose the parameters on rather than using a regular grid. That's fine for small datasets, but it may not be feasible to do that for every processing step in a modern 3D survey. The hope is that active learning could do this for us, automate the process of looking through the dataset to select and prioritize the samples for the human to label. The example I showed earlier was a cats and dogs classifier, but for parameter values, what we often need is not a classifier, but a regressor. As in other branches of machine learning, most of the work in active learning has been done on classification, and many of the algorithms only work for that. But there are some active learning methods for regression. The most popular of these is query by committee. It's a nice idea, and I'm going to explain how it works using this example. The goal here is to approximate the white function. You could imagine that it's an optimal denoising parameter, and each sample might be a trace, a window of traces, or a whole gather. Ideally, of course, we would like to use the optimal processing parameter for every sample. However, we often don't have time for the human to look at every sample and choose the appropriate parameter values there, so instead the human will just look at a selection of samples and will interpolate between those. I'm going to show you the results when we select those samples using query by committee active learning and when we select them using a regular grid. I'm then going to explain how query by committee works. When we select two samples from the dataset, both methods select samples in about the same locations. They're also quite similar when we select three samples. When we select four samples, however, you can start to see a difference in the way that active learning is choosing the samples. And when we get to five samples, you can clearly see that active learning seems to be focusing the samples around the abrupt change in the parameter value. Why is that? Well, the way query by committee works is that you have a committee consisting of several regressors. These could be neural networks that have been randomly initialized, as I used in this example, or they could be something else, as I'll show you in the first break picking example. In query by committee, you fit the committee members to the samples that have already been labeled. And then you use the spread in the predicted values of the committee members at other points as an estimate of the uncertainty at those points. Query by committee then says that you should select the sample that has the highest uncertainty as the next one that you ask the human to label. You'll tend to find that this causes the samples to be clustered around areas where there are changes in preference to areas where the function is more stable. It's a simple idea, but people tend to report that it reduces the number of samples they need in order to achieve a desired level of accuracy. But does it also work for seismic processing? I'm going to test that by implementing query by committee active learning for first break picking. This is a shot gather from the real dataset that I'm going to use to test this. And here are the first breaks. First break picking is one of the most widely used, but also one of the most labor-intensive steps of seismic processing. One method for obtaining first breaks is to manually pick the first breaks on a regular grid of gathers covering the dataset. Each of the traces that you pick gives the picking window for that trace, where the picking window is the largest time window covering the first break, such that if you apply an automatic picking algorithm to the window, it will still pick the same first break as the human did. So for a clean trace, this window can often be quite large, whereas for a noisy trace, it may need to be quite small. We then interpolate these picking windows to all of the other traces in the dataset, and hopefully you picked the gathers on a sufficiently dense grid that these interpolated picking windows still cover the first breaks and are an appropriate length. You can then apply an automatic picking algorithm to all of these picking windows to get the first break picks for the entire dataset. So for each trace, we have two parameters defining the picking window. You could use the beginning and the end of the picking window, but I prefer to use the center of the picking window and its length. I'm going to use query by committee active learning to try to reduce the number of gathers that the human has to pick the first breaks on in order to get good estimates of these picking window parameters for every trace. The committee members that I plan to use are some of the automatic picking algorithms that have been proposed over the past few decades. You could use any of them, but I choose to use the popular Coppens, entropy, and fractal dimension methods. These methods would pick the maximum amplitude for each trace in these plots as their first break pick. They're simple and easy to understand methods, but what I particularly like about them is that they rely on different features of the data to select their first breaks: amplitude, entropy, and fractal dimension. And this causes them to respond differently to things like noise. You can see the advantage of that in this example, where in the part of the gather that's too noisy for the automatic picking algorithms to reliably pick the first breaks, you can see that there's a large disagreement among the committee members about where the first breaks are. In query by committee, This disagreement corresponds to uncertainty, and query by committee says that we should ask the human to label the most uncertain samples. So there's a high probability that a human would be asked to pick the first breaks on this gather. It might have been missed if we were just picking on a regular grid. This is an overview of the method that I propose to use. We begin by randomly selecting one gather from the dataset and asking the human to pick the first breaks on it. This gives us the picking windows for all of the traces in that gather. We then enter a loop where we interpolate the picking windows from all of the picked traces to all of the other traces. So far it sounds very like the conventional method, but now we're going to apply all of the committee members to all of the picking windows. We then select the gather that has the highest uncertainty, the highest disagreement among the committee members, as the next one that we ask the human to pick the first breaks on. If we keep iterating around this loop, we'll eventually get to a point where all of the automatic picking algorithms in our committee agree on the first breaks for every trace. That gives us a lot of confidence that we've got good picking window parameters for every trace. But I'm going to make two more refinements to the method. The first is that I'm going to add another member to the committee. This is an estimate of the picking window center obtained by linear interpolation from the picked traces. So our committee now consists of the three automatic picking algorithms plus this estimate of the picking window center. To see the advantage of adding this new committee member, here's an example. This gather is too far away from any of the gathers that we've already picked for its estimate of the picking window center, shown here in the dashed line, to be a good match with its actual first breaks. By including this new member in the committee, we can now ensure that this gather has a high disagreement among the committee members and so has a high probability of being selected to have its first breaks picked by the human. This means we can ensure that the picking window center always at least roughly matches the actual first breaks for every trace. The second refinement relates to this step of applying the committee members to every gather in the dataset. In theory, that's needed to optimally select the next gather for picking by the human. However, it's quite computationally expensive, so I instead make an approximation. Rather than applying the committee members to every gather, I instead randomly select n gathers from those that have not yet been picked and only apply the committee members to those. But what should n be? To test that, I ran the algorithm for 10 iterations for a range of values of n and recorded the true error on the whole dataset at the end of each. I can calculate that error because I actually already know the true first breaks for every trace in this dataset. You can see that when I do that, the error decreases as we increase n. This is good because it indicates that this query by committee approach of selecting the gathers with the highest uncertainty really helps to reduce the final error. Unsurprisingly, when we give it more gathers to choose from, it does a better job. But you can see that once n is greater than 10, the error stops going down. That's also good because it means that we don't actually need the committee to consider every gather in the dataset every time it wants to select the next gather for the human to pick the first breaks on. We could just give it 10 randomly selected gathers. Just to be safe though, in the remaining results that I'm going to show you, I set n to be 100. Now that we've finalized the method, let's see if it actually works. In this example, I ran the algorithm for 20 iterations and I recorded which gathers were selected. I repeated this 15 times for different random seeds, so in total 300 gathers were selected. I did this for both the active learning approach and also when the gathers were randomly selected. Selecting the gathers randomly is quite like selecting them on a regular grid. In both cases, unlike active learning, they don't use the parameters from previously selected gathers to help choose which gather to select next. As expected, when we randomly select the gathers, they're uniformly distributed across the dataset. But interestingly, you can see that when we use active learning to select the samples, they seem to be clustered around shot 200. Why is that? When we look at a common channel gather for this dataset, we can see that after about shot 200, a new earlier arrival becomes visible, and so there's a jump in the first break picks. We saw earlier that active learning tends to focus on areas where there are changes. Finally, we come to the main result. I again ran the algorithm for 20 iterations, as in the previous example, but this time I recorded the true error on the whole dataset after each iteration. You can see that the error declines quite a bit more quickly when we use active learning to select the gathers compared to when the gathers are randomly selected. This is great news because it shows that you can get to a desired level of accuracy after picking the first breaks on fewer gathers when you use active learning to select those gathers. To summarize and conclude, many steps of seismic processing require parameters that vary over the dataset. Currently, this is often handled by choosing those parameters on a regular grid of gathers covering the dataset. But these may not have been the optimal gathers to choose the parameters for. You might have been able to get equivalent accuracy after choosing the parameters on fewer gathers if you had chosen those gathers more carefully. That's what active learning attempts to do. Query by committee is an active learning method for regression. I implemented it in first break picking. We saw that you need to choose your committee members carefully. I chose to use 3 automatic picking algorithms and an estimate of the picking window center. When I did this, the error declined quite a bit more rapidly than when the gathers were randomly selected. That was great news because it shows that active learning really does have the potential to make seismic processing parameterization more efficient, and to do so with workflows that are quite similar to existing workflows, and to do it without bringing the risk and uncertainty of black box deep neural networks.